Here's a recap of today's lesson on resonance. And to introduce this concept, I asked you to draw the Lewis structure for the ozone molecule, which is O3. So let's take care of that first. So oxygen has 6 valence electrons. There's 3 of them, so we have a total of 18 valence electrons. Doesn't matter which one you put in the center because they're all the same element, but O, O, and O. We need to connect these atoms with a bonding pair. Otherwise, we wouldn't have a molecule that uses up 4 of our electrons, so we are down to 14. Now we can put the remaining, actually not the remaining electrons, but we can give the terminal oxygens the octet by giving them 6 electrons each. That's going to eat up 12 more of our electrons. We're down to 2. The remaining 2 we can put on the central oxygen like that. And now we've used up all our valence electrons. Let's take a look. The octets on the terminal are good. They've achieved the octet. So the oxygen in the center has not achieved the octet. It has 2, 4, 6 valence electrons. We can give it more electrons by taking a lone pair and moving it over to create a double bond or a triple bond if needed. But we only need to do one more, so let's do that. And this is where we got to. If this was an accurate representation of the ozone molecule, then there should be 2 types of bonds, because the typical oxygen-oxygen single bond has a length of 1.5 angstroms, and the typical double bond between 2 double bonded oxygen atoms has a distance of 1.2 angstroms. But if we measure this experimentally, the length is 1.3 angstroms, and I asked you why could that be the case. And so it turns out this is not an actual depiction of the actual molecule. And so Lewis structures is a very simple and very useful model, but like all models, it does have limitations, so we're going to have to compensate or accommodate for what we observe. In this case, a bond length between the oxygens of 1.3 angstroms. All right, so we need to modify this Lewis model, and we have to consider there was no obvious reason to put the double bond there. We could have just as well put it on that side. So let me draw both versions for you. In fact, I'll just draw the other one and copy. This one over from previous. All right, so there you go. There are 2 valid Lewis structures, but neither of them are actually accurate. In other words, the ozone molecule does not have a single bond and does not have a double bond. It has 2 equivalent bonds. So the correct Lewis structure is not given by either one of these. Rather, it's more of a resonance, superposition, or resonating. They both exist at the same time. So we call that resonance. So when there is more than one valid Lewis structure that have the same formal charges for a particular molecule, then the resulting electron structure of the molecule is given by the average of these resonance structures. So we often use a double-headed arrow to represent that. All right, it's important to clarify, this double-headed arrow does not mean this molecule is flipping. Like at one moment it looks like that, and another moment it looks like that. It's rather, this double-headed arrow means that it's the average of both of these structures. All right, so this concept of resonance is needed because Lewis structures are so useful, but clearly it doesn't, it has a limitation here. Lewis structures use the concept of localized electrons, and it's so simple when we consider these electrons to be localized, but in reality, these electrons are shared throughout the whole molecule, and so they're actually delocalized, the valence electrons are. All right, so we went on to try a second problem in class today, and that was using, we asked you to draw that Lewis structure for the nitrate polyatomic ion, which is NO3 with a charge of 1 negative. So I'm going to go over that with you right now. Is drawing the Lewis structure first. Nitrogen has 5 valence electrons, oxygen has 6, and there's 3 of them. Don't forget, some of you forgot to add that extra electron, so that's what's going to give that molecule a 1 negative charge. So that is 18 plus 5, 23 plus the 1 is 24. 24 valence electrons we have to work with. Now the least electronegative of the nitrogen and oxygen is going to be the nitrogen, so put that in the center, and then we'll surround it with the 3 oxygens like that. Now we're going to have to connect these, otherwise they'll just be separated atoms. So 2, 4, 6, let's update the number of valence electrons. Now we're down to 18. Now let's give the terminal atoms, in this case the oxygens, in the octet. Right, so they already have 2 in the bonding pair, so they each want 6 more to get the octet. That's going to use up all 18 of our electrons. So remember, count up your electrons first and make sure you use them all. Don't make up more if you need any, but also don't use less, use them all. So if you notice here, the terminal atoms are all good. They all have the octet, but the essential nitrogen only has 2, 4, 6 valence electrons, so it's not satisfied. We need to get more electrons on the central atom, and when that is the case, you can take a lone pair from the terminal and bring it over, make a double or triple bond if you need. In this case, we do need more electrons on the central nitrogen, so we are going to take that lone pair, could have been any one of these oxygens, and we're going to make a double bond. Don't forget your brackets. There's an extra electron in that whole molecule, so 1 negative charge. All right, sorry, I got interrupted for a moment here. I don't know what the last thing I said, but you could have drawn the same structure with the double bond up here with that oxygen. Right there, and we could have drawn it with the double bond to the oxygen on the left. Now it's important to note that, let's see if I can do this while I'm talking. It's important to note that you can't have resonance if the atoms are in different positions. So just because you have multiple correct forms of a Lewis structure doesn't mean you automatically have resonance structures. It only applies to if the formal charges are the same. Not only that, it just on the structure of the molecule can't be different. All right, so here we go. There's the resonance double arrow there, and double arrow there, and double arrow there.